All right. Hello, everybody. Welcome to the March Rust Gamedev Meetup. So we have a bit of a smaller meetup today. We have 2 presenters. Last month, I think we had like 5. And so I'm going to be doing some more outreach next month. We're going to find some other people to check in with and hear what projects are going on. However, this is not the only Rust Gamedev Meetup from March. We actually are going to be doing something at GDC this year. And so if you're familiar, GDC is a game developer conference in San Francisco. And I've been working with my company to try and get us like a location where we could have like a small little meetup. And so we put together like this sort of in-person meetup at GDC. And hopefully it'll be an opportunity to come out, meet some other Rustaceans, talk about what kind of stuff you're doing in the game dev space in Rust. So I think that'll be really cool. There's also some other meetups going on that have been running for, I think, a few years at GDC from some Rust folk. And so do make sure to keep an eye out if you're going to be at GDC, or if you're just in the Bay Area. Like if you're just in San Francisco, if you can just show up, if you can take a train here, fly here, whatever, then absolutely it'd be super cool to catch up with anybody who's able to be there. So that is happening on the 21st of March. I'll throw the link to this in the chat here, but then you can also find it on the Rust Gamedev Discord. I'll probably put it on the Rust subreddit or Rust Gamedev subreddit as well. Probably Rust Twitter. Sorry, Rust Gamedev Twitter. I keep saying Rust Twitter, but yeah, not upstream of us. Like Rust Gamedev, it would be on all the Rust Gamedev places. All right, so without further ado, we'll hop into the presentations for today. So we will be back in just a second. Okay, Etienne. So you are going to be talking about Mesh to SDF today. If I could just get you to share your screen, I think it's not up just yet. Yeah, but yeah, I saw you post on the Rust Gamedev Discord, I think sometime in February, about this project, and I'm super excited to hear about it. Hopefully, yeah, there's going to be some super cool graphic stuff going on here. So I'll let you take it away.
Yeah, thank you, Forrest, for the opportunity. So hi, everyone. Today I'm going to talk about Mesh to SDF. So basically, like 2 months ago, I was in need of a tool to generate signed distance field from meshes, and I couldn't find any written in Rust. So I had 2 solutions. Either I could use another one written in another language, then find a way to serialize and deserialize the signed distance field, so I could use it in my project, or I could just run my own implementation in Rust, which is what I did, and which is why I'm here to talk about it today. So in this talk, it will be done in 3 parts. First, I will talk about what a signed distance field is, because it's probably not obvious for most of you. Then we'll go through the most common use cases of signed distance field, so you can understand why you might need one in your project. And finally, I will talk about the crate itself, or the couple crate, actually, as you will see later. Before we start, since I said a lot, signed distance field here in the first 30 seconds, and it's actually mesh to SDF and not just SDF. What is a mesh? So in this context, a mesh is the geometry of a 3D model. So it's a list of triangles. So it's not splats, it's not radius fields, it's not anything fancy, just good old triangles in 3D. All right, so what is an SDF? So at its core, an SDF is a function that takes a position as input, so x, y, z here in our case, since we are in 3D, and returns a number. The absolute value of the number is the distance to the surface of the object it represents. So in our case, since we have a mesh, it's the distance to the nearest triangle of the mesh. The sign of the distance is whether the point is inside or outside the mesh. And note that we have an equivalence between being inside the mesh and having a negative result with the signed distance field. So for a circle, it looks like this. When we are inside, the result is negative. On the circle, it's 0, and outside, it's positive. Signed distance fields we only have like so much time available, but just to give a few of them, we have Boolean operations. So here we have 2 objects, a square and a circle. They each have their own signed distance field. And so this is the inside of the circle, the inside of the square. And so if we take the opposite of the SDF of the square, since we have the equivalence between being inside and having negative results, it means that the opposite of a sign distance field is a sign distance field of the complement of the object. If we take the maximum, for the result to be negative, it means it needs to be negative in both objects. So the maximum of 2 SDF is the SDF of the intersection. And likewise, if we take the minimum, it means it's the union of 2 objects. If we combine the first 2 operations, we get the subtraction as well. So it's very interesting, because what we have to note here is that it's free. Like if we have the 2 functions, having for example, the intersection of 2 objects is just one call to the maximum function. It's not expensive. You don't have to do like a complex algorithm. It's just a call to the maximum function, and it's free. Another interesting property is repetition. So if instead of giving the position as input to the sign distance field, we give only the fractional part. So here we have a grid, and you can see the point in the top left is being snapped on the square on the bottom right. It gives us this result. So a point is going to be inside, so negative, if it's inside the circle on the bottom right. So it gives us an infinite amount of circle for free, basically, just because we sent the fractional part and not just the point. We have an infinite number of circle, again, for free. Very interesting. And since we know in which cell the point was before being snapped, we also get instancing like this. We can put some noise in the point before, and we can do fun stuff like this. And the final one I'll be talking about here is the gradient. So here we have a point on the surface of the circle, so its value is 0. But if we just query the value nearby the point, we can get the gradient of the sign distance field, and if we normalize it, we get the normal of the circle on the surface. So it's very, very, very interesting to have so, and it holds true even if we are far away from the circle. So sign distance field, they only gives the distance to the mesh, but they actually also encode the normal of the field and on the surface, and they also encode a good approximation of the projected point on the mesh, just for the cost of 1 number. All right, so yeah, a couple of other things I won't be talking a lot here, but you also have blending between meshes. Instead of doing the minimum between 2 objects, you can do a smooth minimum. And so you have blending between your objects. You can change the metric. Here, I assume we were using the Euclidean distance, but you can use other distance if you want. You have symmetry, distortion, extrusion, etc., etc. There are many, many things you can do with sign distance fields. So how do you store them? You can do a combination of primitives. It's like we did before. We had a primitive that was the circle, another one which was the square, and so we combined them with a minimum function to get the intersection of both of them. So you can do that and add more and more and more of them like this. You can have a grid-based representation, because sometimes you cannot simplify your mesh in just primitives. So instead, what you do is that you take the bounding box of your mesh, and then you discretize this bounding box, and for each point, you compute the distance and you store that, and then you can do trilinear interpolation to get the actual value you want. Or since it's 2024, you also have neural networks that exist today to solve this kind of issue, but they are expensive to compute, expensive to query, so I'm not exactly sure what the use case is for them, but they do exist and they provide the best results if you need them. Sorry for the mouse. All right, so what can you do with a sign distance field? This is the first example. Everything you see here is just one big sign distance field. There is no triangle, no mesh, nothing, just a huge combination of primitives. This is another one, another one, another one. I mean, you get the idea at some point. But yeah, also, nobody said you couldn't have a sign distance field for a fractal instead of just a mesh or anything you wanted. Another one, and yeah, all of these examples work with what we call ray marching. So how does ray marching work? Because you probably heard about ray tracing. Ray marching is different. Let's say we want to render this cute little cloud on the bottom right. As you can guess, it's made of like 4 circles, a union of 4 circles with an intersection with the rectangle at the end. So it's just a combination of primitives, very simple. And we want to render it from the eye point, which you can see on the bottom left. So for a specific pixel, we shoot this ray. And we want to know whether this ray intersects the cloud or not. So the first thing we do is that we query the SDF at the eye point, which gives us this circle here. So we know that within this circle, there is no way there can be an object here. So the ray cannot intersect anything within this circle because this gives us the distance to the nearest element. So we can move forward on this circle, so which we end here, and we can query the sign distance field again, which gives us another circle, and again and again and again until either we hit the cloud or we just go too far away. If we animate it, it looks like this, basically. So sometimes we're going to hit the cloud, and sometimes we won't hit it. The one trick to make it possible is that instead of just returning the distance, we need to return the distance and a base color. And so when we hit it, we have the base color of the object, and we can also compute the normal with the gradient. So we can do the lighting, and we can reproduce what we had before. So this is a cheap way to render a scene instead of doing ray tracing or anything else. Another use case is global illumination. So on the left, you have only direct lighting, so you can see it's very dark. And on the right, you have rays bouncing around, so you can light Shrek the way you want. Global illumination is kind of the holy grail of rendering, and it's a field that is really improving year after year. But nowadays, most state-of-the-art techniques use side distance field at some point in their pipeline. It's very complicated. I won't go into details here, but they do use it at some point. For example, Godot, since Godot 4, they switched to SDF-based global illumination. And another example is Lumen in Unreal Engine. So this is the final rasterized scene in Unreal Engine, but all the lighting you see here comes from this scene. As you can see, it's very rough because it's an approximation. It's a sign distance field based scene that is ray merged, so you can get all the indirect lighting computed here for cheap, and then it is combined with the actual rasterization to get the beautiful lighting like this. So yeah, global illumination is another use case. And the third one we're going to talk about today is VFX and particle systems among them, but VFX in general. This is a screen from Counter-Strike, their new smoke thing. I'm not sure they use SDF in this particular context, so I'm going to switch to a pet project of mine, which is this one. So here in brown, you have 256,000 particles, spheres, that are supposed to simulate a fluid simulation, and you have a dragon here, which is, I think, about 300,000 triangles. I'm not sure exactly. So you cannot, at each frame, query for each particle, each triangle of the dragon. It's not possible. It will be way too expensive. So let's just consider the dragon here. I'm going to hide the AGRI and show this. So this is the sign distance field of the dragon. It is grid-based, so we computed the bounding box of the dragon, and then for each point, we computed the distance. As you can see, it can react to like this, to the transform of the dragon. And so at each frame, let's say I'm going to just to show it works. Simulation, it works like this. Yeah. And so at each frame here, when we're simulating, for each particle, we are going to check if we are within the bounding box of the dragon. If we're not, it means we are far away, so there's no need to query the sign distance field. But if we are, for all the particles in the bottom here, we're going to query the field and see if we are inside or not. And so I'm going to hide the sign distance field, and okay, I'm going to reset the box collisions. And here, if I go here, you can see that they are going to react to the sign distance field. If I show it again, like this, you can see that they are just reacting to the sign distance field information. And so basically they query the SDF, and if the result is negative or less than the particle radius, they're going to compute the gradient, so they have the normal, and they know which direction to go further away and outside of the dragon. And a cool thing is that, let's say I reset, I show the model. It also works if I invert the feed. So let's make the dragon huge like this. And move it a bit. So here, most particles are going to be inside. And if I invert the sign distance field instead, and I resume, the particles are going to be bound inside of the dragon. So it's very chaotic because particles that were outside were just snapped into it very fast, but it's going to count down like this. And so it can lead to very cool effects like this. So this is another use case for VFX on particle systems that are rendered on the GPU only. It's very cheap to do collisions like this. All right, and now, yeah, let's talk a bit about the crates. So I said before, there are actually two crates and not just one, because there is one for the API and one for visualization client I made, so you can see what was going on and validate your fields. So if we just have a look at the API here, it expects as input a list of vertices and indices. So just triangle indices like you would put to WGPU or whatever in the end, just your mesh informations. One important thing to note is that it doesn't care about your underlying math library. You can use an algebra, GLAM, CGMath, or whatever you want. So you don't have to copy your data into something that can be fed to the API. Just makes whatever you want. And you can either generate the field for query points that you choose, or you can do generate on a grid. So a grid-based generation, which will be faster because it's more optimized. Because didn't talk about benchmarking yet, but basically, like most algorithm, you can pick 2 out of the 3 of time complexity, memory complexity, and accuracy. And since this library is fairly new, right now I chose just accuracy and memory complexity, so it can be pretty slow, for example, for the query points, because we cannot induce anything from what they are. So it's just a pretty naive algorithm. But just to give you an idea, for the grid generation on my computer, for a mesh of 1.5 million triangles and a grid of 100 by 100 by 100, so 1 million points, it takes roughly 6 seconds. So since you're pre-computing your field, it's okay now, but it could be faster. I'm working on to make it faster. And the final parameter you can see here is the sign method. I will show it a bit later, but you have 2 options right now. The first one is raycast. So for each query point, you shoot a ray and you count the number of intersections between your ray and triangles of your mesh. And if it's even, you're outside. If it's odd, you're inside. Or you can use a normal check. So you find your nearest triangle and you compute the dot product between the normal of the triangle and the direction between the triangle and your point. And if it's positive, you're outside, negative, inside. But it can be a bit faster, but you can leak negative distance like this, as we will see later. So it's very simple library, very simple API. And with it came a visualization client that I made. So this is another application. It's another crate. It's not mesh to SDF, it's mesh to SDF client. And here we have the cute little Ferris here. But if I display its sign distance field, it looks like this. So green points are outside, blue points are inside, and red are on the surface. You can play with them like this, obviously. Also, I apologize because it's probably getting compressed on your screen, so I'm not sure how it looks like since it's just a point cloud, so many small pixels. It looks good on mine. It will look good on yours if you test it out. But just sorry if it's not looking good right now for you. And so yeah, green outside, you can play with them. You can change the color if you want. I'm just going to hide those that are outside since they're not really important. And you can also display the model and the field. And so for example, here, if I compute, instead of doing raycast, I do a normal check and I recompute it. You can see like blue points here that are leaking outside of the mesh. So yeah, you need to be careful, and that's why you have a visualization client to make sure that nothing is actually leaking outside. But the issue with raycast is that why it's a robust check, it needs the mesh to be watertight, so without any hole, otherwise some rays could leak outside of the mesh through the hole if you have one. So you need to make sure it's a proper mesh because before you use it for this. And also, you have two other render modes here. One is voxels. So it's another use case I didn't talk about because it's not the best method to compute it. But if you want to voxelize your mesh, you can also do it with sign distance field. So here I can play with the ISO surface. So if it's 0, it means the surface of the voxels are the surface of the mesh. But if I increase it, the surface will be farther away until it looks like this, or just smaller until you compress it into just a single blob like this. So you have a voxel visualization, and you also have a ray march one. So it's the same algorithm as I talked before. This is with trilinear interpolation, so classic one. And I also have a tetrahedral interpolation, which is a bit more blocky like this, a bit like Martian cubes. And the final one, which is pretty fun, I like it, is the snap one. So it probably looks very bad on the computer, sadly, so I'm not going to spend too much time on it. But basically, the idea is that you don't interpolate at all in the grid, which means that all the gradients are just wrong, because since there is no interpolation, when you look epsilon away, you have the same result. So that's why it's just blocks and pretty good looking. And so you also can generate your field, choose the dimensions. And so here, for example, there are only 1,000 triangle, but with 1 million points, it took 1.6 seconds on my computer. And it looks like this. So I hope with this, I gave you a good idea of what a sign distance field is and why you might need one in your project at some point, or maybe not. But just to conclude, some references. First two links are the GitHub project and the crate.io link for the library. I often talk about the implementation of this library on Mastodon, so you can follow me there if you want to. The fourth link is a link to the blog of Iniguocules. So if you remember the example of ray matching I've shown before, most of them were done by IQ, which is Iniguocules, is one of the king of shaders. Ray matching was coined by, I think, Donald Knuth in the 70s, but it was made really popular in what it is today, thanks to Iniguocules, who made extensive research on it and on sign distance fields as well. So most of what I've talked about here actually comes from him. And the Shadowtor website that you see here is a website he made also, so you could share stuff like this. So if you liked what I've shared before, just have a look at Shadowtor. It's a goldmine of amazing stuff. And also consider checking Iniguocules' YouTube channel if you want to have a breakthrough of what he did and how he did it in the example I've shown before. And that's it for me. Thank you.
Perfect. Yeah, this was super cool. Kind of seeing the tool and also the theory behind it. We have Ray March in chat who mentioned, like, once you showed that the Ferris model wasn't watertight, they're like, oh my gosh, did I not make it watertight?
No, it is watertight. I mean, I think.
Oh, okay.
The issue is normal, is that there is a triangle somewhere here that is not behaving correctly, but that's a usual case of the issue. So with raycast, there is no issue with this model, so it's fine.
Okay.
There's no issue with Ferris.
So one thing I was curious about, so we talked a little bit about how there was work being done on the CPU and GPU, and I was kind of curious where the boundaries were when you're doing a lot of the calculations and like prepping the model for SDF. Is that all calculations done on the CPU, or is it partly on the GPU?
So right now, computing the SDF is done on the CPU. I'm thinking about computing it on the GPU at some point, but right now it's only on the CPU. So the metrics and the benchmark I gave here are on the CPU. But the idea is that when you computed it, you just fed it to the GPU, and then the GPU is using it. So, for example, the computing here, it's GPU only.
Oh,
once it's done, you query it on the GPU. That's why I said that neural networks I'm not sure what the use case is right now because it's expensive to query, because here I just feed a grid, so it's just an array, and I just query the array. So it's way more simple.
Okay, yeah, I didn't actually understand that step too much, but it makes a lot of sense. Yeah, you put it into this form so that you could have it on the GPU, and the GPU can query it for any work that it needs to do. Okay, yeah, that's awesome. And a question we have here in chat is, was this made with eGUI, and what did you find most difficult with implementing it?
So this visualization client here is made with WGPU, WInit, and eGUI indeed, yeah. Honestly, the most difficult thing to do here is just updating the dependency, because WInit is going to update, then WGPU is going to say, okay, there's an update, so I need to update myself, and then eGUI is going to come later on. So often you have to wait like 2 weeks or 1 week since they're all up to date, and then you need to update them all three of them at the same time and find all the breaking changes you have everywhere for the three of them at the same time. So it's a core to update the project. But other than that, it's really easy to use. If you're interested in having a setup like this for your projects, I did a template in Rust before. So if you have a look at my GitHub account, you have a Rust WGPU hot reload project here that has exactly everything that I talked about here, and also a shader and Rust hot reload. So it's really useful if you want to just play with Rust and WGPU.
Okay, awesome. And yes, talking about the code a little bit here, you mentioned that in the performance side of things, like you were caring more about accuracy and memory complexity. But when it comes to performance, so what do you mean that, like, that's maybe not necessarily like the main focus just yet, but like where do you see there being a lot of potential improvements with how you're doing things?
If we talk about just generate some distance field, so with query points, right now it's just brute force because I don't assume anything about the query points. It could be way faster if you use like a BVH or something like that. So if you just store the triangles in another data structure, an optimized one, so you could query it faster. And for the grid-based SDF, right now it's running on a single thread. So it's 6 seconds on a single thread. So if I could parallelize it, which is a bit tough, but I'm thinking about it. I found a solution. I just need to implement it right now. But it could be way faster if it was running on multiple cores. And that's for the CPU aspect of computing it. And if we could compute it on the GPU, it would probably be much faster again. And so that's if we want accuracy. If we don't want accuracy, there are many ways to compute it, like for way cheaper. An example would be to it's what the Python API does. You render your mesh from one point, another one, another one, another one, another one, and you have basically like 100 depth map, and then you can compute the signed distance field from here. So it's not precise, but you just need to render on the GPU your mesh. It's another solution. I'm not thinking about implementing it, but you have many ways to compute signed distance field. The state of the art is not clear about it. So yeah.
Yeah. Okay. And then I guess one more thing I'm kind of curious about when it comes to working on a project like this. So you mentioned that it's sort of like abstracted away. You don't need to necessarily, or it's more generic over the math libraries that exist, and you can really use it in whatever project that you have. When it came to developing, I assume that most of this is like a lot of math. You're implementing a lot of math. Did you find any complexities with that when it comes to developing in Rust, or was it like just pretty nice and smooth for everything you needed to do?
No, I think it was pretty smooth. I mean, yeah, the idea that instead of relying on one math library, maybe I can show it here if I have it. I implemented a trait here that gives me just what I need. So add point, sub, dot, and such. And then for each library, I implemented for specific implementation, specific library, my traits on them, so I can use it for any library. So the issue is that since I do that, I cannot just implement like traits like add, mirror, or anything. So it's nice to look at, but it's something I could do, so everything could use it. It's one issue that there is no like monolithic math library that everybody uses. It's like everyone uses its own, so it's a bit sparse sometimes. I didn't have any issue on this project, but on a former one, I had issues because I needed some specific tooling, and some of them were only available in an algebra. Some others were only available in ND array, so it was difficult to make them communicate. And I think it's an issue because sometimes you have to copy your data and just allocate twice your memory just to feed them to here and there. So it can be very annoying sometimes. But on this specific project, it was okay.
Awesome. Well, yeah, this is super cool to kind of see behind the scenes of it. And I also, okay, actually, one question I have that I was like, okay, I could ask you after, maybe other people are interested now. What presentation software do you use? Because, oh my gosh, your presentation was so cool to watch.
For the slides?
Yeah.
Yeah, I used this opportunity to learn about motion canvas. So all these animations, it's done in code. It's a YouTuber named Artificial who made this framework. And so it's just code to render this. Sometimes here it's just a huge shader that I wrote that takes here. Sometimes it's just, it's animation. So it was fun to do.
Yeah, I think especially when you're showing the ray moving around and you can see and the math here as well. It just makes it so much more visual. It's like it's like we watched a 3 blue 1 brown presentation. So I think that was very cool.
Yeah, I mean it's a visual field, so you need to be visual too. Yeah, you cannot just put some math here and say, yeah, that's how it works.
Yes, exactly. All right, well, Etienne, thank you very much for presenting about Mesh to SDF. This was a lot of fun. I hope to see some more updates on maybe either integrations or where this can go for like future optimizations and stuff like that. So yeah, thank you very much.
Thank you.
All right, and we'll be back in just a minute with Graphite. All right, so we are back with Kevin, who's going to be giving us an update for what's been going on with Graphite this month. Kevin, I'll hand it over to you.
All right, hello everybody. Back for another month of updates on Graphite, which is our work in progress 2D graphics editor made for vector and raster editing, and specifically taking into account the procedural approach to content creation, but merging that with more of your traditional editor. But let's kind of just jump into a few changes. There's nothing too major this time, but just some additional features and things, as well as some other bug fixes that I'm not even going to mention. But I'm just going to rapid fire jump into a few of these and show them off. So now we have the ability to break closed paths. So previously, if you had a path that was closed, that is like the endpoint connected with its start point, there was no way to actually break it open again. But now you can go ahead and simply, that was because previously, if you deleted a point like this, it would just reconnect. However, now, if you hold down the control key while you hit delete, it will actually delete both sides and make it so the point becomes open again. And you can do that anywhere, and it will reconnect the start points and end points and shuffle them around as necessary to do this. And then also, if you want, you can do Control-Shift-Delete, and that will break the points apart, but not actually delete the adjacent edges. So pretty simple, but that was necessary to be able to actually reopen a point that previously was closed. And then, of course, you can always close them again with a pen tool by clicking on both sides. Yeah. Next one, rapid fire. Sliding point insertion. So now, with the path tool, this is the tool that you use to actually edit existing paths, existing points, and as opposed to the pen tool, which is what you use to draw new points. You can now, with the path tool enabled, simply click on an edge, and then you can slide this point around, and then click again, and you now have a new point inserted on the edge there. So this allows you to click once, and then move it. Previously, we had the ability to double click, and you can still, of course, do that, which basically just doesn't slide it anywhere, but now you can click and then slide. So nice and just a nice quality of life improvement, and hopefully improves the clarity. Now we also have the node graph box selection. So when we open the node graph, we have all these nodes here. As a quick overview, if you're new to Graphite, basically what's special about Graphite is that we still have layers, but the layers are basically just exporting data that is fed into them from their left side here. So on this left side, we're feeding in this chain of nodes. So we have the shape itself, we have the transform that gives it the position and rotation and scale. And then we have a fill, which in this case is white, but I'll make it sort of a color here. And then we have the stroke, which is the thickness and the color as well, as you can see when we modify it. Yeah, but these are the nodes, and now we have box selection. So you can simply click and drag multiple, and that makes it much easier to move things around like this. Another simple feature, but definitely a quality of life improvement. We also now have work saving every 30 seconds, so I can't show you this, but basically, previously, if we ever had a crash, then your work likely was not saved unless you had previously done something that would cause the work to be saved, such as reloading the page. But now it'll save automatically every 30 seconds, so you're never going to lose more than 30 seconds of work. Now the pen tool has the undo ability and redo ability. So previously, if you were drawing something, you couldn't control Z segment by segment. It would actually just make the entire thing disappear or the entire thing reappear. And now you can still go, even after you finish the path, you can still reconnect like that. And then also we have the freehand tool, which can reconnect things as well. So on the endpoints, now I'm using the freehand tool. This is the tool for drawing random things with a polyline. But you can now reconnect onto the ends. We have this little dot, this little square here showing the endpoints, and you can even do this on shapes that are made not with the pen tool, or not with the freehand tool. Or I can even make an ellipse, and then split the ellipse, and now use the freehand tool to reconnect these points as well, or even do it on one of these more styled points, or more styled shapes, I mean. And this, in particular, is very useful for the use case of this demo artwork. Whoops, wrong one. It should be this one. So this one is our Christmas lights here, and these are procedural, so they will be updated automatically as you continue drawing additional segments. But let's say I want to now just draw like this, and that makes it nice and simple to do. Basically use the freehand tool as sort of a data source to provide some paths for your procedural editing. Okay, that is all of the rapid fire feature progress of the past month. But I do have a couple announcements. One is that we have switched over to the release series of Alpha 3. Previously, we were calling this Alpha Milestone 2, and now that we've finished basically the past year of development, this was where we called it Alpha Milestone 2. We're renaming that just to Alpha 2, and now we're on Alpha 3, and this will encompass the next year or so of development. And this is going to be the year that we basically focus on procedural editing, and particularly the more advanced parts of procedural editing that you might be experienced with. You might have experienced with if you're using Blender geometry nodes, for example, where we have the spreadsheet, and that allows you to have attach attributes, which are basically columns in that spreadsheet, and you can basically attach pieces of data to it and then process that data and do a lot of very advanced things. So that's the theme for the coming year, as well as raster-based editing, where we're going to be making some significant improvements to the overall raster workflow. So that is the Alpha Milestone 3, or Alpha 3 beginnings. Additionally, one last announcement on our blog, if you check this out, if you are a student or someone basically looking for an internship for the summer, you can get involved with Graphite in the coming month and kind of show off your abilities, and then do a proposal for one of the projects that we have available. So we have a big list here of some project ideas, and each of these project ideas on this page, I'll just scroll through them real quick. They talk about different things that you could work on for basically an internship over the summer. And then thanks to Google Summer of Code, they are sponsoring the stipends for students to work on these projects. And they'll basically be able to get paid for an internship over the summer to work on these projects. So if this is exciting to you or interesting, go ahead and read this blog post and get involved, and basically use the coming month or so to work on both getting involved with some existing bug fixing and building some small features. And we'll use that to, of course, to see how well you work with us. And then you can do a small proposal, which basically just means submitting kind of your expected timeline of different things throughout the summer. And then we will consider you for working as one of our accepted students. So yeah, definitely get involved on our Discord server if that's interesting to you. And yeah, get involved with the information on screen. That's all for today, and I guess we'll look forward to seeing you next month.
Perfect. Nice and clean. Got some cool features there. I like the list of projects that you have for GSOC. I think super cool to kind of have some of those there. Now I did see some in the list. I'll go check out later myself, but so a lot of them look like sort of tool implementations or like one thing that would be nice to have in an editor but isn't there just yet. And so you have these for GSOC like potential participants or proposals, but do you also sort of have a list of this like roadmap wise where maybe some like the items down the line that wouldn't be as good as a GSOC project but could be good to just have someone sit down and start implementing over a series like the time span of like a month or two? Do you have any of these ideas written out, or is that kind of more just for the GSOC?
Yeah, these are definitely sort of the larger scale projects. Most of them were intended to last about 350 hours, which is the duration of the GSOC internship. But basically, these are also available to anyone who was interested in just working on a relatively large project. And then some of them are a bit more research oriented. So for example, one of them involves porting the libra library from C into, actually it might be C++. Yeah, I think it's C++, into Rust, and kind of making a whole new library based upon that. So that's sort of research oriented in the sense that it's more, a little more experimental. And then another one is based upon knowledge of machine learning, and that one is kind of researching the best way of bringing all the world of Python's machine learning systems into a more deployable, portable, Rust-based ecosystem, and in a way that can be run both locally and in the browser, even for at least the more lightweight models, and also on the server, and kind of doing so in a consistent, deployable, portable manner. That's another example of a relatively research-heavy project that I don't think anyone actually this year has shown interest in working on that one, but that is also a good thing that people who are specifically interested in machine learning could work on even outside of GSOC if they were just interested in contributing that.
Yeah, true. And I know there's been like work in, I forget what the exact name is, but sort of taking LLMs and being able to run them with like a Rust, I don't know if it's interpreter, like what the term is, but so it would be a similar idea to that, where you want some model that's better for specific artistic things to be able to, I especially with web GPU, be able to be run in the browser alongside Graphite. That's sort of like the idea.
Exactly, yeah.
Yeah. Okay. Yeah. That's super exciting stuff. And so, yeah. And the last thing I want to touch on quickly, will Graphite be at GDC this year?
We are planning to be there on Friday.
On Friday. Okay.
So
Cool.
definitely be sure to give us a shout. Give us a reach out, and we would love to meet up with you if you're there on Friday.
Perfect. Yeah, I definitely plan on checking in with y'all. That'll be very cool to kind of see you in person. But yeah. Anyways, it sounds like we're pretty good for. Features this month. Super excited to hear where Graphite is in the next month. And we did just get a question come in, so I'll just pull it up here. So KittyCAD is using a DSL and ML to produce 3D models. Is that sort of what you're thinking about? Or I guess like what other inspirations do you have for models in the browser? Like what kind of cool stuff have you seen?
Oh, sorry. The word model, I was just thinking of 3D model, and my brain went in that direction. Could you repeat the question now that I'm thinking about machine learning?
Yeah, sorry. Wait, sorry. So I think, yeah, they're saying KittyCAD is using a domain-specific language and machine learning to produce 3D models. But then I guess what you're talking about is machine learning models that can be used to enhance your, I guess, like artistic or creative capabilities, maybe.
Okay. Well, yeah, I don't know actually quite where the question asked, because it did actually mention 3D models, which was where my brain initially went. But more generally, I can talk about the overall plans for that, for 3D for graphical models. So those fall into a few categories. One is image generation, so that's segment anything. That's stable diffusion basically, and then there is, and that's also useful for in painting, for example. So if you have an existing image and you simply want to cut out a particular object or person or something that you don't want in your scene, you can simply mask that person out and remove them. Or you can also mask the other direction and, for example, uncrop an image and take an existing image and then basically generate the borders, things that are around the outsides of that. So those are all very useful use cases for image generation. The other major one is segmentation. So this is basically being able to automatically rotoscope or automatically cut out the boundary of a particular subject. So if you have a car, you can basically just click on the car and have it automatically select the car or a person, and hopefully even ideally even select their hair, because that is the very difficult part, is having those really fine pixels that that just correspond to those fine semi-transparent things such as hair. Ideally having a really good model that's able to do that, and segment anything seems to be the best model that exists at the moment. And then finally, another one is depth creation, or depth, whatever you would use the word for that. So a depth model is able to take an existing image and generate basically the Z buffer for that. And that can be very useful for different procedural effects. Or if you want to, for example, you want to make everything transparent in the scene that is not between some Z depth minimum and some Z depth maximum, you can basically cut out in a scene just those pieces. So if you're able to use machine learning to infer the depth of the scene, you're able to do some really interesting effects like that. So those are the main ones. But then, of course, there are a whole bunch of additional ones that will, I'm sure, come out in the future, or ones that I'm not even aware of at the moment, but they're beginnings of some research. But those are kind of the main ones that are very useful, because you can make even very traditional tools like the magic wand tool and use that for selecting things using the segmentation models. You can use kind of the in-painting features of many graphics editors for using that with the stable diffusion things. And then the depth models are useful even perhaps for like tools that are built into the editor for basically selecting things based upon their focus depth or their focal length distance from the camera.
Yeah, and I think I love that idea of, or
yeah,
I was just
all
like
the procedural things.
Yeah. So like you have all these like separate models that you use to do something, and sort of like a package manager that you could say just like quickly download this model. You could have like a quick demo of like showing off what it's doing, and then very easily, because I imagine a lot of these models will either be open source or have like open source versions of proprietary models that some company might make.
Exactly. Yeah. We would be implementing the ones that are already released publicly for those purposes.
Yeah, that sounds like a lot of fun. So it'd be very cool to see once that
we just need people who have machine learning experience.
That is fair. All right. Well, yes. Thanks, Kevin, very much for presenting and showing off some of these new features, and very excited to hear how GSOC goes. Did you all do it last summer?
We did not. This is our first summer.
Okay, super cool. So yeah, hopefully you're able to get some participants with some good proposals and work on some very cool things. It'll be awesome to hear about some success stories from that.
Yeah, definitely. Looking forward to it.
Awesome.
Okay.
All right.
Thanks everyone for tuning in this month.
Yes, all good. And we'll catch you next time, Kevin. Cheers. All right, so that is all for this month. I'm going to try and make sure that I get the blog posts posted with the YouTube videos for anybody who's interested in sharing any of the presentations we had this month or last month. And so, yeah, with that, hopefully next month we can have some super cool projects to check out as well. And we will see everybody then. Catch you later. Wait, before I go, I should mention I'll be hopping over to the Rust Gamedev Discord if anybody wants to hang out in chat for a little bit there. I always forget to mention that.